We've been learning about different types of radioactivity. Big question, why are some nuclides radioactive? Some atoms are stable and others are not. And then why do they undergo the different types of decay that they do? So let's think about what the nucleus is. The nucleus is a collection of protons and neutrons, right? And so protons and neutrons together are called nucleons. They're like the residents of the nucleus, right? The nucleons. How do those get held together? Did you ever wonder about that? Because it's positive protons and they're like all squished together. And don't positive charges repel each other? Yeah, they do. But there's this sort of mysterious thing called the strong force that holds it all together. That's a fundamental force of physics that acts at very short distances. So the stability of the nucleus, any nucleus, is a balance. So we have repulsive coulombic forces, so those are the forces of repulsion between protons because of their like charges. And then we have this attractive strong force that happens between all of the nucleons. Any questions? So neutrons are important in stabilizing the nucleus because they attract other nucleons without repulsive force. So we've got attractive force, the strong force between all nucleons, and then protons are repelling each other. So if you have more neutrons, then you're going to be more stable. Due to energy levels that are occupied by the nucleons, you get to a point where the energy payback from the strong force no longer compensates for the high energy state that neutrons that are added need to occupy. So protons and neutrons occupy energy levels in a similar way to electrons, right? So the lower energy electrons are close into the nucleus, and then as you add electrons, they're higher and higher in energy. And so the same is true for protons and neutrons. The great thing is we're not going to study their energy levels. So what we find is that this ratio of neutrons to protons is an important number in determining nuclear stability. This is a graph of number of neutrons versus number of protons for all known nuclei. So each yellow dot is a known nuclide. And the stable ones are in green. So here we see a trend in stable nuclei. And so we can look at the ratio of neutrons to protons is the slope of this line. We see that in the smaller atoms, it's pretty close to 1, whereas when it gets up here, mercury 200, the stable one is at 1.5. Above 83 protons, there are no stable nuclei. They're just not. So the type of radioactivity will depend in part on this ratio. So if we look at the ratio for a given nuclide, if it's out here, then it's going to be unstable. If it's in this area, it's more likely to be stable. And we can predict that the types of radiation that will be given off will be related to this ratio. So if the N to Z ratio is too high, I forgot to mention, this little line here, this area, is called the valley of stability. So you could think of that as, this is hills or mountains, and this is where the river is down the middle. That's the valley of stability. That's what they call it. So if we have nuclides above the valley of stability, they've got too many neutrons. So they tend to give off radiation, radioactive particles that will convert neutrons into protons, which lowers the ratio. And that type of radiation is beta decay. When you have an N to Z ratio that's too low, these nuclides have too many protons. And so they tend to convert protons to neutrons by positron emission or electron capture. And that will raise the N to Z ratio. Alpha decay also raises the N to Z ratio, but the effect is smaller. So there are two methods to predict the type of radioactivity. And I don't consider this to be a hugely important topic. I want you to give it a shot. There will be a question on the exam, but it's not a big deal. So one way you can do this is you can look at figure 20.5, the valley of stability. The other method is you can compare the mass number of the nuclide in question to the atomic mass listed for that element on the periodic table. The atomic masses on the periodic table are the average of all the stable nuclei. So you can look at the element on the periodic table and determine its ratio, N to Z, and that's going to be about right. So then you can compare the nuclide that you're looking at to the average and see if it's going to be stable, or if not, what kind of radiation it's going to emit. So let's look at ruthenium-112. So if we find ruthenium on the periodic table, we see that the stable atomic mass for ruthenium is 101.7. This tells us that ruthenium-112, being higher, must have too many neutrons. And so therefore, we would predict beta decay. We can also just actually calculate those ratios. So ruthenium has 44 protons, right? So if we have 112, that's the mass number, minus 44, 68. Oops. 68. So neutrons to protons. 68 neutrons to 44 protons. 1.5. So the atomic mass here is the average atomic mass. The atomic mass is going to be very close to the mass number. So this one has more neutrons than this one does. This one is a mass number of approximately 101. So if we subtract 44 from that, we get 57, and, whoops, I always forget which one goes on top. N to Z would be neutrons, 57, divided by protons. .3. So we can get this estimate of a good N to Z ratio for ruthenium from the information on the periodic table. The average atomic mass we can use as the mass number, subtract the number of protons, that gives you the number of neutrons. Neutrons divided by protons. 1.3 is good for ruthenium. So for ruthenium-112, we can calculate the number of neutrons, divide by the number of protons, and see that this is 1.5. So that's higher than what's good for ruthenium. So it needs to decay in a way that it comes down on that graph. So that's going to be getting rid of neutrons. So N to Z is too high. They tend to convert neutrons to protons by beta decay. Any questions? Okay, let's practice. Predict whether each nuclide is more likely to decay via beta decay or positron emission. Well, let's first, before we start looking at these, when does beta decay happen? Too many neutrons or too many protons? Too many neutrons, right? So too many neutrons or too many protons for the positron emission, right? So this is high N to Z ratio, and this is a low N to Z ratio. Well, lead 192. On the periodic table, we see that lead is number 82, and its average atomic mass is 207.2. So is this isotope nuclide going to have a higher or a lower ratio? I don't expect that to be immediately obvious. Why is this mass number smaller than this one? Is it because of difference in protons or neutrons? It's neutrons. This one has fewer neutrons. We're looking at neutrons over protons. These guys have the same protons, right? Because that's what makes them lead. So if PB192 has a lower ratio, that means it's got not enough neutrons or too many protons. Does that make sense? So would that be beta decay or positron emission? To our summary here. So here's the beta particle, right? In the beta particle, this -1 tells us that we're losing a neutron. So a neutron becomes a proton. In positron emission, the opposite happens and a proton becomes a neutron. So you can, at the very minimum, what you need to do is memorize these little symbols here. So you could make up an equation like this. So this is beta decay. Do the equation, and now look, did that change the number of protons? Did it make it bigger or smaller? How does that affect the ratio? For this one, we see that the number of protons goes down, which means the number of neutrons relatively goes up. And here, the protons go up, the relative neutrons go down. So that's something you can kind of figure out if you need to. How about lead 212? Well, we already established that the stable mass for lead is about 207. They've got the same number of protons. So this one has more neutrons, right? That's what makes it heavier. So too many neutrons is going to be beta decay. A question like this on an exam is going to be similar to this, where we give you limited choices. We're not going to include positron emission and electron capture because those do the same thing. We're going to give you one of each. How about xenon 114? Well, let's find the stable mass for xenon, 131. So this xenon atom then, does it have too many neutrons or too few? It has too few neutrons. So it has too many protons. So that's going to go by positron emission. Any questions? There'll probably be one question like that on the exam. Yeah?
So there's no reason to compare it to the average mass of like the other ones, like how we did for the first one.
Well, we can calculate the ratio for both of these. We could do that. That's what I did in the other one.
Yeah. So
Yeah.
there's no real reason to compare.
You don't have to, no,
Okay.
because you can just see that this number is smaller because it has fewer neutrons, right? So then, if it doesn't have too many neutrons, it must have too many protons. But if you can't remember how to do that, you definitely can calculate the ratio for each of them. So you can find out which one is the ideal for that element by looking at the mass on the periodic table. And then compare the nuclide you're looking at to that. Any other questions? No. That's the result of me skipping around. Magic numbers. That sounds fun, doesn't it? Yeah, it's not exactly fun. So the ratio of neutrons to protons is important. The actual number of protons and neutrons also affects the stability. And so some of this stuff is people are they're looking for patterns in the information. It's like, okay, these guys are stable, these guys are unstable. What kind of patterns can we find? Can we find a rule that predicts anything? Don't really have a rule, but some observations. So a large number of stable nuclides have both an even number of protons and an even number of neutrons. So 157 stable nuclides are even. Only 5 are odd. That's a big difference. And the even-odd combinations are also significantly smaller than the even. So there's something special then about having even numbers of nucleons. And we can explain this because nucleons will have a tendency to pair together, much like electrons pair together. So when we learned about electron structure, we learned that electrons can have opposite spin, and they'll spin pair in an orbital, even though they're both negative and shouldn't want to be with each other, right? So protons and neutrons can do that as well, and so that's why an even number is more stable in general than an odd number. So nucleons occupy energy levels, a lot like electrons do. And just like atoms with certain numbers of electrons are especially stable, like the noble gases, right? 2, 10, 18, 36, 54, 86 electrons. Those are especially stable. Those elements are almost unreactive. There are some numbers similar to that for nuclides that are uniquely stable. And so these are called magic numbers. You do not need to know these magic numbers. If the number of neutrons or the number of protons is 2, 8, 20, 28, 50, or 82, it's an especially stable nuclide. If n is 126, and notice that all of the magic numbers are even. I will not give you a magic numbers question on an exam. But it's kind of interesting, and this has to do with energy levels within the nucleus. It's like we had enough trouble with the electrons, thank you, let's just not talk about the nucleus. So any questions about that? Radioactive decay series. So when a radioactive nuclide decays, it does not necessarily decay into a stable nuclide. It will decay generally into a more stable nuclide, but the nuclide it decays into may also be radioactive and unstable. So this is showing the decay series for uranium-238. All atoms above 83 protons are radioactive. They decay in one or more steps. It's usually alpha and beta decay. If they build up extra energy, then gamma decay will happen to get rid of that extra energy. And the decay will continue until you get to a stable nuclide. So uranium-238 goes through a whole bunch of steps. Goes to thorium-234. I can't remember the name of that one. Pa-234. Uranium-234. And so going down to the left, we get alpha decay. Down to the right is beta decay. Because this is like that valley of stability graph. We've got number of neutrons versus number of protons. So we're seeing the N to Z ratio change as we get down here. And so it's going to end up at lead-206, which is stable and is not going to decay any further.